anything in this cup here?
No, anything.
Alright.
Sure they can.
Okay. If you haven't already, it might be, you know what? I'm just gonna do it. Grab a calculator. It's LIM.
It's true. When I first saw you, my heart stopped.
Alright, so the first function we're going to look at today is this absolute value of x minus 3 over x minus 3. And we're looking for the limit as x approaches 3. Okay, so a little refresher from yesterday. What number is my c value? 3. C is the x value. That's the focal point of the limit. So what the x is getting close to. Do I care what happens at 3 for the limit? No. I do not care what happens at 3. So a lot of things could be happening at 3. You could have an asymptote at 3. You could have a hole in the graph at 3. You could have everything filled in at 3. We don't care what happens at 3, just what happens as you get close. Go ahead and graph that or put it into your function, or into y equals. Go to your math button. It's the ABS function. Yeah. 162?
I don't see ABS.
Oh, there it is. I can't reach it.
Found it.
Yeah.
Does it still have to be in like parentheses?
Okay. Your total was 162, and others was 189. I don't know. Yeah. Did you find it? No, we haven't. In the past. I haven't. Maybe Galloway did, but I didn't last year. Do you have a small class? Oh, I can find out from her. You do too.
I'm not really sure what I'm doing.
Oh.
That sounds surprising, Nathan.
I don't know. I think it's a major one.
Did you both parentheses around these?
Huh?
Parentheses.
I think so.
Yeah, she
I
is.
do.
You offered. You won't feel guilty.
Scrap it?
No, actually, you can't.
Okay. Okay. Not sure that's right.
Alright, do it. Yeah. Okay, bye.
It's fine.
Alright.
You can do whatever.
That was just Mr. Gubino complaining that he lost the food drive. Okay. So, does anybody have...
Is it really?
Yes.
That's awesome.
He's like, well, it's 12.
How many kids does
You
she
said
have?
Did he win last year? He's won every year for 12 years. That's the first year he hasn't won.
Oh.
I tried to call you earlier. Sorry to not interrupt right now, but now it's the only time I had.
You
I
should
have
hit me up more often.
I will. 16 to 20 pound turkey for you, if you want it for whatever you're collecting things for. Oh, well we have.
He told me to call you and let you know.
Okay. I have enough turkeys for everybody.
You have enough turkey?
Yeah.
Okay, I'll tell them to get some.
Okay.
My brother gets one every year from his company and they're not
Sorry.
Okay.
So he wanted to know if we could
Okay.
use it anywhere. So.
Thanks for letting me know. Okay. Right, do you have a graph? Do you have a graph?
Now I put my feet up on the chair.
Okay. Does everybody's graph, now that we're back together, does your graph look like that? Okay, does everybody... Oh, here's a little bit different. My calculator uses the letters ABS when you put in the absolute value, which it looks like it just turns into the value bars when you put it in. Okay. So that's what your graph should look like. Make sure you put the top and the bottom in parentheses. So if you didn't get that graph, that might be what happened. So what's happening to my function here? It's making a jump, right? So there's a little bit of a break. It still passes the vertical line test. It's still a function, but there's a break at what point? At 3. Okay. So we're going to go ahead and draw that as best we can. Now, if I plug 3 in here, what happens? I get 0 on the bottom. So technically, my function does not exist at 3. So when I actually graph this by hand, at 3, I need to put open dots there to signify my function does not exist at 3. But it has that jump or break in the graph there. Okay, so now we're going to look at limits with this type of graph. Alright, so my focal point is at 3. Now we would need to look at values to the left. So let's say we set up my function here. Some values that are really, really close to 3 are like 2.9, 2.99, right? 3, and then what's some really close values to 3 on the other side of 3? 3.001, 3.01, 3.1. Okay, so those are some really close values. If we wanted to get really close to that, we would. So if you look at your table, and I don't have, can I borrow yours? If you look at your table, and you put in 2.9, 2.99, even if we went a little further, 2.999, you get, what is your y value? Visually, is that what's happening here? Yeah, all the y values there are -1. And then what should happen for 3.01 and 3.1? Be 1. What's happening at 3? An error. Okay. Now, a limit exists when your numbers from the left and the right, so as you get closer to this focal point from both directions, that they're squeezing towards one value, that they're going to meet up at one value. As a reminder, like yesterday, for this problem, when we squeezed towards the number 2 as my focal point, the y values were getting closer and closer to 0.25. They're squeezing closer to 0.25. Here, they're getting closer and closer to 1. What's the problem here? Are they zoning in on one y value? No, they're not. So in this case, this limit does not exist. So there are situations where the limit doesn't exist because the definition of limit is a single y value that y approaches when x approaches a certain c value.
Go over that again. Like, I get how it's squeezing into one little number. Like, what were you comparing it to? Like, can I see that one problem?
Yep. Like this one, where from the left and the right, they're getting closer and closer to 0.25.
Keeps going.
Yeah.
Okay.
But like here, there's a total jump to a completely different number. Like they're not getting closer to, they're not narrowing down to one number.
Oh, I thought it was getting closer to 0 or something like that.
If it was getting closer to 0, then your y values would look like negative. Yeah, it would start. The actual negative values would get closer and closer to 0. It'd be like -0.01, -0.001, that kind of stuff. So that's not what's happening here. So this one does not exist. And if you want to write yourself a little note here, the actual limit does not exist because the graph and the table, so graph/table, since that's what we're working with here to look at limits, our graphs and tables, the graph and the table do not approach one y value. And I should identify that as x gets closer to 3. So it isn't approaching one y value as x gets closer to 3. Now, let's say we change this problem a little bit. We're not going to write this down, but let's just think about it. And we change this to x approaching 2. So now, or let's do something different. Let's do x approaching -3. So if negative 3, 1, 2, 3, if that's my focal point now, what are the y values to the left of negative 3? Negative 1. What are the values directly to the right of negative 3? So would it have a limit at negative 3? Yeah, it would have a limit of negative 1. So just because at x approaching 3 you don't have a limit because they don't match up, they don't meet up, the two sides, doesn't mean that you don't have a limit anywhere. You still have limits in lots of different places.
Hello?
How does she hear that? You didn't hear that?
I'm driving to Ionia.
What the fuck?
Alright. I think we're done with that one. Alright, let's go ahead and in y equals put this one.
I think it's safe to say that nobody heard that.
What?
Oh,
What, Nick? Why are you muttering?
I said I can't. I think it's safe to say that nobody heard that but you. But then Selena said that she heard it.
Oh, the phone?
Yeah.
Alright. So in y equals, go ahead and put 1 divided by x squared. And then graph it and try to have a good window. Alright, so this is the graph that I got. Does that look similar to what you guys are getting? Okay, so without getting too much into it, we actually have two asymptotes here. You have a horizontal asymptote that follows the x-axis, and then we have a vertical asymptote that follows the y-axis. Okay, so we're going to actually draw that in or sketch it just to show or have on paper what we're looking at. And then your graph kind of curves up like this and curves like this. Okay. And then, as we've been doing, we're just going to make a short table of values here. Since we already have the function in my calculator, it's easy to look at this. 0 is my focal point, so I need some really close values to the left of 0 and some really close values to the right of 0. Negative 0.999. Negative point. Wait, 0.999? 0.001. Yeah, 0.999 is really close to negative 1. And this would be let's go 0.01. Okay? And then two values close to the right of 0 would be 0.01 and 0.001. Okay, so we're going to go ahead and go to my table and put those in. So negative 0.01, negative 0.001. It doesn't really. What do you mean?
Would the 0.001 go beside the 0? Isn't that close?
Yeah. Yeah, I would. And then to the right. Oh, you're talking about these. Yeah, these should be switched.
10,000.
Okay, and then you have 0, and then you have 0.001 and 0.01. Okay. Now, when I look at these numbers, at negative 0.01, my y value is 10,000. Then at negative 0.001, my y value is what?
A big one.
186, which means 1 with 6 zeros after it, which is 1 times 10 to the 6, which is 1 million. Good. So we go from, in a thousandth of a place here, we go from 10,000 to 1 million. Now, what if I went any closer? What if I went negative 0.0001? What's going to happen to my y value? It's going to get even bigger, right?
You're probably going to get 2 digits.
Yeah. At 0, you have an error. And then on the right-hand side, your values end up being the same, 1 million and then 10,000. Now, what this means is in this case, we don't have a limit either. Because a limit is a single y value that both sides are squeezing towards. But what's happening to your y values here? It's going on to infinity. They're getting bigger and bigger and bigger. So visually, does that make sense? As you get closer to 0, what's happening with your graph? You're going up. You're not meeting at any y value here because are these two sides ever going to match up, really? No, they're just going to keep increasing forever and ever. So in this scenario, because of the definition of limit, this does not exist either because it's not a single y value. It's not squeezing in on a number. It's exploding as it gets closer to 0. You're getting larger and larger. So we would say, and this might help some of you where you might need some help. As x approaches 0, and some of this terminology I'm going to start using is on purpose because you're going to hear it more and more, so I want to get used to it. As x approaches 0, f of x, which is the graph of the function, increases, and I don't know if I've used this term before, but without bound. Increasing without bound basically means that you're going towards infinity. There's no cutoff point. There's not a point where it's going to curve another direction. It's just going to keep growing and growing and growing. There's no limit. So we have towards infinity that's increasing. And then is infinity a single y value? No. Infinity is a concept. So this is why, in this case, you don't have a limit. So, because infinity is not a single value, the limit does not exist. Okay. I have one more case to look at, and this is the fun one to graph.
You can leave. Okay. She doesn't
Nah.
like Toy Story.
Why are we talking about Toy Story? We were most definitely talking about increasing without bounds. Not Toy Story. Oh, infinity and beyond. Duh. That's fine.
You don't belong in America.
What?
You almost cried at the end of the third one.
I did cry. I saw twice in that movie. Oh yeah. There.
You don't belong in America either. She doesn't like Disney movies. Emily. What?
Yeah.
It's okay, Emily. Stay strong.
Not bad enough that Mr. Human hasn't seen any. She doesn't like him.
All right.
I thought it was a great cut. So did he.
Okay. Here's the last example we're looking at today. Make sure when you graph this that you're in radians mode, just so everybody's looking at the same graph. Okay, and if this is what your graph looks like, I want you to zoom in a little bit. So I'm going to hit zoom in and make sure, zoom in, and I want to make sure that my little cursor guy is on the origin. And press enter. And I might even zoom in one more time and see what happens. No, I'm just going to stop there. Okay, so this is zoomed in twice. Now, this is the close-up. This is the close-up of what you're seeing. If I zoom out one more time to what I was seeing before. So, like, in this area here was all that craziness that you just saw on the screen. Okay? This is called oscillating behavior. It's almost like you've taken a bouncy ball and you've thrown it as hard as you can, and it just keeps bouncing back and forth, back and forth, back and forth, back and forth between two pieces of glass or something. Okay. If we look at the table for this, because our focal point's at 0, right? So if we look at the table, it should already be set up for that. Look at what's happening with my values. You jump from positive to negative to positive to negative. Is it going to be narrowing down to one single y value? No. Because there's so much erratic behavior there, you're not able to focus in or squeeze towards one single y value.
Do you have to draw it?
Yeah, but I'll show you how to draw it.
Just draw random craziness
And then craziness.
Oh, that's good enough for
Yeah.
me?
Just to show that, like, in that section in the middle there, it's just like crazy behavior. It's just bouncing back and forth, back and forth.
Yeah, that's
Just scribble. So, in this case, as x approaches 0, f of x oscillates. And oscillates is just a fancy word for, like, bouncing back and forth. So it oscillates between negative and positive numbers. The limit does not exist. Because you don't approach a single y value. Now, I know some of this for some of you is probably getting repetitive, but there's a reason why it's repetitive, because I want it to stick in your brain. So, you probably realize that when teachers repeat something more than once, it's probably something that you need to pay attention to more than others. Alright, so some follow-up questions here. Can you have a limit without having a value at a particular point? Did we have functions, like in the last 5 examples that we did we have an example where we had an error message at our focal point, but we still had a limit? Yeah, that happened right here, right? At my focal point, we had an error, but I still had a limit. Okay, so yes, you can. Do you think there are situations where the function will have an undefined value and not have a limit? Did we have a situation where we had an undefined value, where there was an error, and we did not have a limit?
Yeah.
Which one was that one?
Example 3.
Example 3, it was the one where it, like, broke, right? So there will be situations where it has an undefined value and it does not have a limit. So you have both kinds. You have ones where you will have a limit without a value at that point, and where you won't have a limit. So yes, there are. What would the graph look like, and what basic function must be involved? In this case, whenever we have a break like that, does anybody remember what kind of function that's called? Piecewise. Good. Good. So yes, the graph would have to have a break. And those are called piecewise functions. Okay. So there are some common types of behavior. We actually did 3 examples today on those common types of behavior when limits don't exist. The first one would be that you have a break in the graph where x is approaching. That was like example 3. So, whenever you have a break in the graph and the break happens at the focal x value, the c value that you're looking at, you're not going to have a limit that exists. The second situation, what was the other one we looked at? Not necessarily just 2 asymptotes, but where it has an asymptote, where they increase or decrease without bound. So we just call that unbounded behavior. I did not spell that right. Unbounded. Threw an extra N there. Unbounded behavior unbounded behavior always happens when asymptotes are involved. Okay. Now, if there are asymptotes in the problem, that doesn't necessarily mean that the limit doesn't exist. Because if you, I'm going to flip back really quick and then flip. When we did example 1, we had an asymptote in that one, but were we able to find the limit? Yeah, because where was my focal point? At 2, right? So at the hole in the graph, not where the asymptote was. So just because there's an asymptote, don't automatically write it off as there's no limit, because it all depends on where that focal point is that we're looking at. Okay, so that's the next one. And then the last one, what do we call this kind of behavior up here? Oscillating behavior. So if you have oscillating behavior, and again, it's all dependent on where x is approaching.
When you say x is approaching, are you talking about the x, the arrow, and then the...
Yes, that point, that value. Alright. So that's where we're stopping with the notes today. We're going to watch that short clip again like we did yesterday to hopefully solidify it.